Have you ever thought about a world where we don't just repair the human body, but rebuild it from scratch? Well, today, we're going to dive into the incredible field of biomedical engineering and see exactly how scientists are designing, building, and yes, even printing brand new parts for us.
I mean, just think about it. From a simple paper cut to a broken bone, our bodies have this absolutely amazing built-in repair kit. But sometimes the damage is just too much, or disease takes over, and that system just can't keep up. So that's where the engineers step in and ask a really big question. If the body can't fix it, can we?
And look, if you think this is all just science fiction, let me introduce you to the famous Vacanti mouse. This was back in 1997. Scientists literally created a biodegradable frame in the shape of a human ear, put some cartilage cells on it, and tucked it under the skin of this mouse. The mouse's own body supplied all the nutrients, a new ear grew, and just like that, this one experiment blew the doors wide open for what we thought was even possible.
So that one wild experiment perfectly sets up our big challenge, right? How do we go from an idea to a living, functional part that a person's body will actually accept?
This is the field that's taking on that exact challenge. Biomedical engineering. It's where all these different worlds collide. You've got mechanical engineering, material science, and a deep understanding of biology, all mashed together to solve some of the toughest problems in medicine.
So, where do you even start? Well, just like any big engineering project, whether you're building a bridge or, a bladder, it all starts with your materials. You have to pick the absolute best building blocks for the job. In our world, those building blocks are called biomaterials. And you can see from the definition here, there are two really crucial ideas. First, non-viable. That means the material itself isn't alive. And second, it has to interact with biological systems. See, a biomaterial can't just sit there. It has to actively work with the body.
And we basically have two main flavors here. We've got natural biomaterials like collagen, which are awesome because our cells already know what they are. The catch, they can sometimes kick off an immune response, and honestly, they're not always that strong. Then you have synthetic biomaterials, like special polymers, which we can engineer to be super strong and easy to produce. But our cells might not recognize them, which can cause problems. It's a classic engineering trade-off. The real holy grail is creating hybrid materials that give us the best of both worlds.
Okay, so we've got our material picked out. Now we need the blueprint. How do we design a part that not only works the right way, but also fits the patient like a glove?
One of the most brilliant things we can do is just copy nature. It's called biomimicking. I mean, nature has had millions of years to get these designs right. By studying the structure of something like bone, from its big overall shape all the way down to its tiny microscopic network, we can learn how to make our own designs so much better. But for a replacement part, one size does not fit all. It has to be a perfect custom fit. And this is where modern medical imaging has been a total game changer. Using a CT scan, we can take a whole series of 2D X-ray slices of a patient's body and then digitally stack them all together. What you end up with is a super precise 3D model of the exact part we need to make.
All right, we have our specialized materials and we have a perfect digital blueprint. All that's left is to bring it to life. It's time to hit print.
This is where 3D printing, or what engineers call additive manufacturing, has just completely changed the game. So instead of starting with a block of material and carving something out, a 3D printer does the opposite. It builds the object from the ground up, one microscopic layer at a time. It's the perfect way to create those really complex, porous structures our cells need to grab onto and grow.
And the process itself is actually pretty elegant. We take that 3D model from the CT scan, we feed our special biomaterial into the printer, and we let it go to work. The printer then just meticulously lays down the material, layer by tiny layer, until our physical scaffold, the whole framework for our new body part, is finished.
And I want to be clear, this isn't just a cool theory. This stuff has produced life-changing results. Get this, in 1999, taking what they learned from that ear on a mouse experiment, a team at Wake Forest printed a scaffold of a bladder. They coated it with the patient's own cells in a lab, and then they successfully implanted it. The body grew around the scaffold, which eventually just dissolved, leaving a brand new, working bladder behind. I mean, come on, that is absolutely incredible.
Okay, so the part is printed, it's seeded with cells, it's implanted. But now comes the final and honestly the most critical part of the whole thing, the ultimate test. How will the body react?
At the end of the day, everything comes down to this one crucial property, biocompatibility. This is the whole ballgame. It's not enough for the material to be non-toxic. It has to get the right kind of response from the body, one that encourages healing and working together, not rejection and fighting back.
What's so amazing is that the body basically treats a well-designed implant like a natural injury, and it kicks off its own healing process. First, hemostasis stops any bleeding. Then, inflammation brings in immune cells to clean everything up. But here's where the magic happens. During proliferation, new tissue and blood vessels actually start growing into our scaffold. And finally, in the remodeling phase, that new tissue matures and gets stronger, becoming a fully integrated part of the body.
And you know, the impact of this technology is just massive. It goes way, way beyond medicine. As this quote points out, the ability to print complex things on demand is changing everything from making airplanes to consumer products. But you could argue that its most profound use is in rebuilding the human body.
So we've gone from picking out materials and drawing up digital blueprints to printing scaffolds and then letting the body itself finish the job. We're already engineering skin, cartilage, and bone with these exact methods. So the question isn't really if we can engineer body parts anymore. The real question is, what's left? As we look to the future, what will we engineer next?